Alright, today we're going to look at even and odd functions. We're going to look at classifying whether a function is even, odd, or neither. And then we are not going to do determining the one-to-one today, so we're going to scratch that off. I'm going to say that for the first day. So looking at a graph, if we're going to try to tell if a graph is even or odd or neither, we need to look at symmetry. There's two types of symmetry that we're looking at. We're looking at being either symmetric with respect to a line or a point. And that will help us decide if something is even or odd. So if we're looking at a line, what does that mean? Well, it means we could take our function and fold it in half, and it would be the same on both sides. So that first example right there is symmetric to a line. So that one is symmetric to a line, and that line is our y-axis, or where x equals 0. So it is symmetric about that line, the y-axis. If we look at that second example, if I drew a line down there and folded it, it would not be the same. It would actually be the opposite of being symmetric about that line. But if I take a look at a point, so if I take a look at that origin right there, if I was to spin that around, spinning that shape around that point, it would look the same. And that's spinning around. And that's spinning around is exactly the same. So that means it is symmetric about a point. I can tell because when I'm rotating it. So this is symmetric around the point. And that point being the origin. So how does that help us with even and odd? Well, we can determine if a function is even or odd by looking at its graph. If a function is symmetric with respect to the y-axis, where x equals 0, that's that line, then it is an even function. If a function is symmetric with respect to the origin, 0, 0, then it's an odd function. Let's take a look at these examples. Example 1. Can I fold it in half? Well, if I drew a line right down that, or if I had a little short piece of paper and I could fold it, it would be symmetric. Both of the sides would be equal if I folded it. So this is an even function. If I look at number 2, if I drew a line down that y-axis and I fold it, it is not going to be the same. They're going to be in the opposite areas. So I have to look at a point. So if I take a look at a point, just this point right here, that origin, if I spun that around, would it be the same? And the answer there is yes. If I spin that around, it would be the same. So it is an odd function. Now look at number 3. If I look here at the y-axis, if I fold it, is it going to be the same? No. Doesn't work. What if I went with the origin and if I spin it? If I spin it, would it be the same? No. So you really got to think about that thing, but if you spun it, it would not be the same. So this one is neither. And sometimes it helps if you just take your paper and spin it. It would not be the same. One, I can see that this one looks like it has an open circle, and that one doesn't. So that right there is an issue. And this one's going through it too, and that one at 1, that would also be an issue. So what about algebraically? Algebraically, we're going to take in our function, we're going to replace x with a negative x. And then we're going to clean it up. If when I plug in the negative x, the function ends up being the same, then I have an even function. And if it ends up being the opposite of the original function, then I have an odd function. Let's go ahead and try it. So I'm going to plug in a negative x, which means I'm going to have 2 times a negative x squared plus 4 times a negative x to the 4th. There's enough to stop and think. I'm going to square the negative x, and when I take it negative x to the 4th power, it ends up being positive. Anytime I'm taking a variable or a number to an even root, I'm going to get a positive. So 2x squared, because this ends up being positive 1x squared, plus 4x to the 4th. Because when I take a negative x and I take it to the 4th power, it stays positive. Now, if I look at that, it's exactly the same as the original function. So the f of x equals the f of the negative x. When that's the case, then even. Let's take a look at number 2. A little divider here. So we have so much room. I'm going to do the f of a negative x to the 3rd power minus 6 times negative x. Alright, now, f of a negative x. Negative x to the 3rd power is going to say negative, because negative times negative times negative is negative. This will be a negative x to the 3rd power. And then a negative times a negative right here. Negative 6 times a negative x is a positive 6x. I'm going to look at that and compare it to the original. This one was positive. This is opposite of that. This one was negative. And that's opposite. So, if that f of a negative x is actually equal to the opposite of f of x, so which one is it? It's odd. It's not, when I plugged in that negative x, I ended up getting the opposite, which is what it says. If I get the opposite, then it is an odd function. Now let's try number 3. F of a negative x is equal to negative x squared. Put the whole thing in, because I don't think negative x squared minus 2 times negative x plus 1. So a negative x squared becomes a positive. That's the same as that. Negative 2 times the negative x becomes a positive. That's the opposite. Plus 1. So when I'm looking at that, I don't have the exact same function, and I also don't have the opposite function, because if I had the opposite function, I would have had to have a negative here and a negative there, so it would have been the opposite of that function. So in this case, I'm not fulfilling either one of these. So I am either. Okay. So let's think about our 10 basic functions, whether they are odd, even, or neither. And you can refer back to day 1 notes if you need to look at the graphs. Some of them are graphed, their graphs are on the wall, so we can also look at those. If I'm thinking about odd, that means I would have to be symmetric about a point, remember that. Evens are symmetric about the y-axis. So I'm going to start with my evens because I think they're easier. Quadratic is equal. Oh, we can see. Quadratic. Who else is even? Absolute value, if you look at that, if I could fold that one, that's going to be also even. You can fold it in half. Nothing else, I think. Nope. Now, if it is symmetric about the origin, so linear one, if I look at that one, if I spin it, it would be the same. It's not a reflection, so my linear would be odd. If I look at the reciprocal, or we'll call it our rational, give it a broader name, that one would be odd because I can rotate it. It's symmetric about the origin. Cubic one, if I rotate that one, it would be symmetric about the origin. Cubic. How about our cube root? Yes, I spin that one because it's actually very similar to the cubic. So it would be symmetric about the origin. Cube root. The square root. Neither. Definitely can't fold it on the y-axis and that's the same, and I can't rotate it. So it would be a neither, square root. Let's see what else we have. Exponent. Nope, there's only one part of that graph, or only one piece, so there's nowhere for it to be symmetric to as far as the y-axis or a point. So, exponential. Log. It's the inverse of the exponential, but it's definitely not symmetric around the y or the origin. Log. What about our trig one, our sine? Look at that one. If you rotated it, it would be the same, so that means it is odd. So the odd ones, linear, rational, cubic, cube root, and sine, there's 4 of those. The even ones are the ones that are symmetric about the y-axis. That's our quadratic and our absolute value. And the ones that are neither are our square root, our exponential, and our logarithmic. A couple examples go through. We're working on plastic. So we're always looking at, is it symmetric about a line or a point? So you can do both, just to check. If I draw a line there and then fold it, would it be the same? That one I think you can see pretty easily. So that makes it even. Now you could also, if you wanted to, draw the point there and see if you rotated it, would it be the same? And it would. If you rotated it, that would be upside down. Looking at number 2. So let's think about drawing a line. If I draw a line and I fold it, is it going to be the same? No, it's actually going to be the opposite. That kind of is a hint there. It's going to be the opposite. So if I put a dot on the origin and I spun it, just think about spinning that, and then it would be the same when I spun it, when I rotated it. So it is an odd function. Number 3. Now, if I draw a line down and fold it, no, it's not the same. That one's going up, that one's going down. Here's where you have to be careful. You might look at that and think that, so it might be tempting to look at that one and think, well, that's the cubic, it's just shifted up. But keep in mind that it has to rotate around the origin. If I rotate this about the origin, is it going to be the same? And the answer is no, it will not be the same. So it is neither. Okay, number 4. Should look familiar to you? Maybe. Does anybody know what it is? It's one of our trig functions. If I cut it down the middle and folded it, would it be symmetric? And the answer to that is yes, it would be exactly the same. So that is an even function. And that is your cosine. If I looked at the point, just to verify, if I spun it, would it be the same? And no, it would be upside down. Now, looking at the Next one, our sine function. Hopefully that looks familiar to you. If I folded that in half, would it be the same? No. Actually, the opposite on both sides. But if I rotate it around this point, you can see that it would be the same. So that makes it off. Now let's take a look at some algebraic ones. Remember with the algebraic ones, you plug in a negative x. So the f of a negative x is equal to negative x squared plus a negative x. Negative x squared is going to be a positive, so it's x squared minus x. So I'm looking for two things. I'm looking to see if it's exactly the same. Is it exactly the same? Is the f of x the same as the f of a negative x? Answer to that, no. Not the same because we have a minus there. So then the next question is it opposite? Is the f of x equal to the opposite? Is that exactly the opposite when I plug that in there? It's not. For it to be the opposite, it would be a negative x squared minus x. So this one is neither. Now, sine and cosine, we actually looked at the graph, but let's look at them without the graph. Let's look at if we did it algebraically. So we did the f of a negative x. So that would be equal to the sine of a negative x. Now, obviously you could look at the graph and just say what would it be, and you would see that it would be the opposite. But let's take a look at just the sine of pi divided by 4. So we'll look at that. Or 45 degrees. So, if I'm looking at 45 degrees, thinking about my unit circle, right? 45 degrees. I'm going to look at the unit circle, that means that it's 1 unit. I went with the 45 because it's a 45, 45, 90 triangle, which makes it an isosceles triangle, which means that this is also 1, which means that this is the square root of 2. So think about this on our graph here. So the sine is opposite over hypotenuse. So the sine of, oops, let me change the rate of that. Sine of 45 is equal to the opposite 1 over the square root of 2. Okay. What if I'm doing negative? What if I'm doing negative pi? So what's the sine of negative pi over 4? Because this was the f of x right here. This one, and there's one different color, is negative, the f of a negative x. So negative would be down this way, negative pi divided by 4, which means that my angle is 45 still, because I'm doing pi divided by 4. This is a negative 1. That's how far that goes down, negative 1. And this is square root of 2. This right here is still 1. So my sine of 45 degrees is equal to opposite over hypotenuse, negative 1 over square root of 2. So are those the same? They're not the same. It's not even. Is it equal to the negative? So it's not the same, it's not that one, but is it equal to the negative f of x? And yes, the answer would be it is. 1 over square root of 2, negative 1 over square root of 2. So that makes that off. Which we already knew from the picture. Because we could say pi, there it is a pi, and there's the opposite. So this one equal 1, this one. Now let's look look at our cosine. Now you might say, we already know the cosine is even. We already know that the cosine is even, but let's go ahead and prove that, and we'll do something similar here. So we're going to do pi divided by 4. That's 1 monophase because it's an isosceles triangle, or a 45 degree. So looking at cosine, do f of x in red. So unit circle, 45 degrees. This is 1. That's 1 because I'm doing an isosceles triangle. And this is 3. So the cosine of pi divided by 4. Now cosine is adjacent over hypotenuse. That's 1 over the square root. Now if I want to do the opposite one, we'll do that one in green. Cosine, let me erase this down here. Cosine, negative pi divided by 4. That means I'm going in the negative direction, moving this way. This is a negative 1. This is still 1, that's its length. 1. This is square root. So that would be adjacent is 1 over square root 2. They're the same. They're the same. That's this right here. The f of x is equal to the f of a negative x. That means the truth is good. Now, we go back to the picture since we have a picture here. We can see that. Look at those two. They're the same. Cosine of pi and the cosine of negative pi. Same thing with that, the same. 2 pi, negative 2 pi.